All right. So first up, sort of gonna set the scene, explain what sort of context we're operating in and what we're generally aiming to do. So we're gonna imagine we've got a bunch of random variables, x1 through xn, and I'm going to call these observables. There's more than one way to apply the stuff we're going to be doing today, so this could mean different things in different contexts. But a sort of prototypical example that we're going to be using is you've got like some ideal gas, very simple example, and you've got like little chunks of this gas, and x1 through xn are going to be the low-level states of these chunks of the gas. Okay. And we'll probably go over some other examples along the way.
Chunks of space or groups of?
So like states of particles in this little chunk of space or space-time, if you want. You can do that either way. Okay. Next up, we're going to have two agents modeling this system. Okay. And key thing is they're both going to have the same predictive distribution over the observables. So we're going to have agent 1 has model M1, agent 2 has model M2, and they both agree on the distribution of x. So we're going to have P of x given M1 equals P of x given M2. But these two models are going to be modeling the system in two different ways. The way we're going to talk about that is by saying that they're using different latent variables. So M1 is going to be over both x and a latent variable or bunch of latent variables called lambda. And M2 is going to be over the observables and a bunch of latent variables called, actually let's call this lambda 1 and lambda 2. Lambda 1, lambda 2. And these could just be totally different things. There's no particular, they're not even necessarily in the same ontology. They could have different type signatures. For instance, it could be that model M1 is modeling this as some generalized version of rolling a biased die a bunch of times, right? So it's just saying all of these are independent draws from the same distribution. Whereas model 2 maybe is modeling them as in some sort of Markov random field, right? So there's like a graphical model in there. So like totally different things could have totally different latent variables. And the thing we're going to want to do is try to give some sufficient conditions under which there's like a nice way to translate between these two latent variables. So we want to be able to like take the sort of stuff that M2 is used to using to model the world and translate it into the stuff that M1 is using to model the world and vice versa. Okay? Make sense?
So M1 and M2 could give different causal models of the world.
They don't have to be causal necessarily, just like different models of the world. They just have to agree on the observables.
Different factorizations of the same
yes,
distribution.
Very much so. Good.
But they're still the same probability distribution.
They still give the same distribution over x. So another way to think of this would be maybe you've got two neural networks and you're training them on the same data set. And you know they both get like basically similar loss on the data set. So they're like making the same predictions, right? But they have totally different internal structure, totally different architecture, different stuff going on inside. All right, good setup. All right. The conditions of interest, there's going to be two interesting conditions. One of them I'm going to call the independence condition. The other one I'm going to call the invariance condition. So the independence condition, actually I'm going to switch colors here. This is our mental model. I'm about to like write some variables and then talk about how they would fit in over here. So first I have the independence condition that says x1 through xn are independent given some latent variable lambda. Second, I have the invariance condition which says, I guess I'll draw it this way.
Wait, this lambda is one of the models lambda? Or
I'm going to get to that. We're going to be interpreting these as like either or in the future. So like we'll be mapping these lambdas to those lambdas in several different ways. For now, they're just some latent variables. All right.
Can I ask you to repeat the first question? The first was the independence, lambda?
Yeah, I'm about to repeat these quite a bit. Don't worry. So this one I'm calling the independence condition. The other one I'm calling the invariance condition. Why do we call them those?
So that's what is xi and xj? I don't see that.
Some chunks you should
I
write.
can't make out.
Hold on. I'm about to explain.
Yeah, John, could you write a little bit bigger? I don't think
All right, I'll write them really big on this board because we're going to use them a bunch. Everybody see that? Okay, good.
What is this subscript? Subscript?
Yeah, so the subscript here, this is I bar, indicating all the parts of x except for I. Okay? Give me a minute, I'm going to explain what they mean. So the independence condition, let's take the ideal gas example. The independence condition is saying conditional on this lambda, each of these different little chunks is independent. So for instance, in an ideal gas, an ideal gas, typically if we condition on the temperature and these chunks aren't too close together, then that will hold, at least it's a very good approximation. And we're going to get to approximation later. Then the invariance condition is saying that if I throw away any one of these variables, so like ignore any one little chunk of this gas or whatever, then I will still have basically the same information about lambda prime. So again, in the case of an ideal gas, the thing has to be at equilibrium, obviously. Ideal gas is not very interesting unless they're at equilibrium. But assuming that's true, you can calculate the temperature from like any little chunk. So if you throw away one, you're still going to have basically the same estimate of the temperature. Make sense? So those are two conditions. We're saying these lower level variables are independent or approximately independent given one of our lambdas. And the other lambda you can calculate from a subset of the chunks, or ignoring any one chunk. And at the moment, we're imagining these are two different, these conditions are applying to two different lambdas, lambda, lambda prime.
In Charles' example, the invariance is only approximate, right?
In almost all the cases of interest, the invariance is going to be, both of these are going to be approximate. We're going to get to that.
Is that meant to be one of the variables in your model, or is it meant to be the separate variable?
That's what I was about to say. So we're about to walk through a proof that involves treating these as two different variables, but then the main interesting result is going to be what happens when both of these conditions apply to the same latent.
But one latent within your model, not all of the latents in your model.
Correct.
Just to confirm, when you talk about independence, you mean pairwise independence?
I do not mean pairwise independence. I mean that xi is independent of xi bar, conditional on lambda for all I. So it's not just pairwise independence, it's straight up proper independence.
So lambda is pairwise, it's just like factoring.
Well, no, it's pairwise and also like any three of them and also any four of them. It's stronger than pairwise.
Completely fair.
Other questions?
Sorry, what was again the difference between lambda and lambda prime?
These, for now, are just like two arbitrary latents that satisfy these two conditions. And we're about to walk through a proof that will just apply to any two latents which satisfy these two conditions. Okay?
Two latents, each of which one satisfies one of these conditions.
Yeah. So we've got lambda satisfying one condition, lambda prime satisfying the other. Okay?
Okay.
And can you could you go back to the original thing about these two different models? How does that fit?
We're going to do that in like a minute after we walk through the claim here. We're going to use these two assumptions. I'm also going to add one more assumption, which is going to turn out to be not super load-bearing later, but just going to stick it on the board sort of arbitrarily for now. We're going to assume that the two latents are independent given x. Note that this doesn't imply that they are living in the same model. So for now, we're imagining that we have lambda and lambda prime living in just one model. So these are like two different latents in one agent's model for now. Now, here's the big claim. If these apply, then we have, make sure I get the directions right here. David, yell at me if this is wrong. Leave lambda prime goes there. That look right? Okay. So the idea is we can take sort of...
I think it might be swapped.
Swapped?
I think so. Prime, the invariant should produce an X-latent, right?
Nope, it's not swapped. All right. So the idea here is I can take any sort of information which is invariant under, any latent which is invariant under dropping a variable. So like any quantity that I can compute from like sort of arbitrary subsets, right? Or arbitrary subsets of size n minus 1 of the x's, right? Take any such quantity.
Robust latents where you can figure them out even if you knock out a little linear data.
Exactly. Take any latent along those lines. And I can take any other latent which induces independence between all these things. So any latent which conceptually contains all the information that's distributed across more than one place. I can take those two latents, and this one tells me everything about x that one does. So if I know the value of the one that's inducing independence, then learning the value of the one that's invariant in this sense tells me nothing additional about x. Okay? Yes?
Sorry, just to confirm, even the second condition, you can have a subset xi at the bottom, so it could be x1, 17, 18.
No, that would be a stronger, well,
Single one.
In the exact case, yes. In the almost all the interesting cases are approximate, and then that is different. You'll get a weaker approximate. It'll adjust how strong the approximation
So
is.
you have a single variable.
Yes, just a single variable at the bottom here.
What does the arrow mean?
Right, notation. This is Bayes-net notation. For instance, this one is saying that I can factor p of x lambda prime as p of lambda prime, p of lambda given lambda prime, p of x given lambda. And similarly, each of these is saying that the distribution satisfies an approximation.
Is there a theorem that these three conditions imply the bottom diagram?
Sure is. We're about to walk through it.
Oh, I see. You're assuming all three of these conditions.
All three of these conditions. Here's the argument. We're going to do the whole thing graphically. So step one is using these three conditions, we can sort of stitch together the diagrams and form this. Okay, so what's this saying? Conceptually, this is saying, based on this diagram, one way I could sample lambda x and lambda prime would be to sample lambda, then sample x conditional on lambda, then sample lambda prime conditional on x. And furthermore, a way I can sample x conditional on lambda is to first sample lambda, then sample each of the x's independently. So that's this part of the diagram. And then to sample lambda prime, given x, I can sample lambda prime just by looking at xi bar. So that gives us this diagram here. To sample the whole thing together, I first sample lambda, then sample all of the xi's independently, and in particular xi independent of xi bar, conditional on lambda, and then sample lambda prime, conditional on xi bar. Okay? Then next step, staring at this diagram, if I condition on both lambda and lambda prime at the same time, I still get xi independent of xi bar.
Why do you only have one arrow going to lambda prime from one axis and not from all of them?
Because this condition is saying that to get the distribution over lambda prime, I only need to know xi bar. I can ignore xi. So I only need the arrow from xi bar. I don't need the arrow from xi.
Oh, that's bar.
Right. So next step, if I condition on both lambda and lambda prime, then I can see that xi bar and xi are still independent.
Can I ask maybe a simple question about just the premise of invariance?
Yes.
Why do we have to explicitly encode the invariance? Doesn't that arise from just saying that x bar gives us lambda prime?
X bar.
And not saying...
What do you mean xi bar gives us lambda prime?
Sorry, I'm talking about the second diagram in the
Yep.
notation.
This one?
You're having that xi bar, an arrow from that to lambda prime, and I'm wondering why do we have to encode the second bit of the diagram there?
This part?
Yeah.
So in Bayesnet language, if I just have this diagram, then xi could be, it's not saying anything about xi, and it could be that xi is connected to both of these. So I have to include it in there to say like xi is independent of lambda prime given xi bar.
So arrows mean conditional independent statements.
Well, more like cuts mean conditional independent statements, but yeah.
Yeah, I
could.
mean, the arrows are sort of like Markov kernels. So, like if we just had, I mean, we would say lambda prime is stochastically a function of xi bar, but then it might be that if we also do x, that would change our distribution on lambda prime.
Yeah, that's right.
Mm-hmm.
All right, back to proof. You will need at least a little bit of familiarity with Bayesnet's diagrams to read off this from that, but if you have a little bit of familiarity with Bayesnet's diagrams, you can glance at this guy and see that if I condition on lambda and lambda prime, xi is still independent of xi bar, therefore this diagram applies. And furthermore, I can also see from this diagram that lambda mediates between xi and lambda prime. So I have lambda prime, lambda xi for all I. And I can put these two diagrams together, combine those two, well, 1 plus n diagrams really, to conclude lambda x1 through xn lambda prime. So the way we do this is we say, well, if I have this for all I, all of these are for all I. If I have this for all I, then conditional on lambda and lambda prime, all of the xi's are independent. And the distribution of xi given lambda and lambda prime is the same as the distribution of xi given lambda. So that allows me to like pull this lambda prime up there. And then that this is actually slightly stronger than the thing we're proving. We've proved a little bit extra. We have lambda prime. Yeah, that was a terrible prime. Lambda prime, lambda x. Okay? All right, so that's the main like foundational piece we're gonna need. Now we're ready to start tying it back to that stuff and state the like big use case. Yes?
Why did you use your secret third condition?
So the secret third condition is used when sort of stitching these two together to make this diagram.
Right, because otherwise you couldn't put the
Exactly.
Yeah.
All right, I'm gonna erase the giant diagrams over here. All right, so now we're gonna go back to our two agents with their different models. And we're gonna say, suppose that agent one looks at their lambda one under their model, and they see that lambda 1 satisfies both of these two conditions. What would that mean? So now we have a single lambda satisfying both conditions, so lambda x1 through xn, lambda, which way did I draw the arrow? Xi bar, xi for all I. So this means, if this lambda is satisfying both of these conditions, first of all, that implies I can pick any lambda prime I want, take any other latent, so for all lambda prime, such that lambda prime also induces independence. So for any lambda prime that satisfies this, I will have lambda satisfies that, so according to this guy, we will have the invariant guy over here, so we'll have lambda, lambda prime xi. I've apparently switched which one's primed. That's fine, we're going to switch them back in a moment. That's lambda, lambda prime x. And for all lambda prime such that...
Wait, why is it, how do you get the, so you're using that proposition, but how do you get the part where conditional in x, lambda, and lambda prime?
We're going to get to that momentarily. That's the right question to ask. So what this is saying is, if I have a single lambda that satisfies both of these, first of all, that lambda is minimal in a certain sense. In particular, if I look at the set of all latents that induce independence, then this lambda is the smallest of them. It induces independence, and for any other latent which induces independence, lambda can contain no more information about x than lambda prime does. Right? So it's sort of, in some sense, the least informative about x latent that induces independence. So we're going to call this the minimal latent condition. On the other hand, I can say, all right, lambda satisfies this invariance condition, and it's sort of maximal among the set of all latents which satisfy an invariance condition, because like for any other latent which satisfies invariance condition, lambda contains all the information about x that that other latent does. So this one is going to be a maximal latent condition.
I'm confused about the implications now.
Yeah, hold on. First I'm going to address Vanessa's question, then we're going to get to what this looks like for our two agents. So Vanessa was asking, wait, don't we need this other condition here? And it turns out we get this condition for free, because if both of these conditions apply, then lambda is a deterministic function of x. And in the approximate case, we'll say that lambda is an approximately deterministic function of x, and therefore an approximate version of that diagram applies.
So there's no...
In fact, I'm going to write down the deterministic function right now, just so we have it on the board. I'm going to write... There's a thing I'm sweeping under the rug here that I don't really want to dig into right at the moment. So I'm going to write this instead. This is...
Could you write a little bigger, this equation, please?
Yes. So I told a small white lie a moment ago. It's not that lambda itself is a deterministic function of x. Lambda can also contain like some independent noise in it that has nothing to do with x.
Yes.
So what this guy right here is doing is just saying ignore the independent noise. Just worry about the part that's relevant to x. And that part.
So it's deterministic after throwing out the independent noise.
Yes, and after throwing out the independent noise, you'll still have a latent satisfying these conditions. So usually what I say is we want to put it in standard form relative to x. Take like, yeah.
Yeah, okay.
Right, so this is equal to?
This operation throws away independent noise.
Yes.
Interesting. Yeah, very interesting.
So this guy is a product on I, x maps to p of xi,
Independent with
little
respect
xi.
to x.
Yeah, hold on a sec. And then that in turn is product on I, x maps to p of big xi equals little xi, given x, y, log. No, wait, I forgot the I bar here. No, I didn't forget the I bar. Right. I'm going to leave that on the board. Not actually going to explain it at the moment. We will probably come back to it later. The important thing for now is there is like this deterministic function, so we get this condition for free. And now on to...
Wait, so lambda isn't literally a deterministic function, or deterministic plus noise that doesn't depend on it?
Yes. So what we have is we can think of this expression as a standard form for lambda. So we can take any latent satisfying these two conditions is sort of deterministic plus some independent noise. This guy throws out the random noise and gives you a sort of standard form latent that satisfies these conditions and doesn't have any, independent random noise in it. Okay, back to this guy. So we've now said for absolutely any latent, satisfying this condition, we get this mediation. For absolutely any latent satisfying this condition, we get that mediation. In particular, this means if we have two latents that both satisfy the natural latent conditions, then they have to be isomorphic. Or rather, their normal forms here have to be isomorphic. They have to give you the same distribution over x. And that's the thing that I want to use as a conceptual building block for bridging between one model and another model. So the idea here is if agent 2 is modeling this, yes?
Well, go ahead now.
All right. If agent 2 is modeling this system, if agent 1 is modeling this system and they find a latent or a latent over part of their model is natural, i.e. satisfies these two conditions over some part of the system, then anywhere in agent 2's model, where agent 2 is defining some latent that satisfies either one of these conditions, we get a mediation statement. So we can say if agent 2 is using a latent that satisfies the independence condition, then we get this mediation. Notably, this independence condition is exactly the condition you would usually get out of a deep generative model. So typically, for instance, if you look at a deep image generator, what it's doing is...
But something here is a little weird because the lambdas that different models have, how do they even leave with the same probability? Correct.
I think I want to not unpack that yet. You should bring it up again later. Right, where was I? So this condition, this is like a thing that's very typical for generative models, right? You're like modeling the observables or the data or whatever as having been generated from a bunch of latent variables, and all of like the individual pieces of data or individual components of a data point are independent given those latent variables. So this is a standard architecture. If we have something like that, then we can say basically that lambda's relationship to x, so M1, the lambda from M1's model, the one that satisfies these natural latent conditions, has to sort of factor through the latent being used by this generative model, for instance, right? So basically what it's saying is I can go look at the latents in the generative model, and I will find that my latents that are natural, that satisfy these naturality conditions, tell me no more about x than lambda prime does. So this sort of, it's like strictly weaker. It's not like these two things are sort of telling me different things about x, right? Everything captured by lambda is also captured by lambda prime. Yes?
Maybe it isn't time yet for this, but I mean, I feel like, I don't know, these conditions are very hard to simultaneously satisfy in the exact way. And so it's sort of all about the approximation.
Yep,
and
that's
I feel
correct.
Like just don't have a sense of the approximation. Maybe that's the next part of the talk.
Yeah, that'll probably be part 2. I assume we're going to break it.
All
Okay.
the way through now, so would now be enough time for a break?
All right, I think I'm going to address the thing Vanessa just asked, and then we'll break. So the thing Vanessa just brought up is that these lambdas are living in 2 totally different probability spaces. The way that I want to handle this, or the way that I do handle this, is to say that sort of what defines a latent. It's not really that like a latent is a random variable. Really, what defines a latent is the conditional distribution p of lambda given x for that latent, right? So a latent is defined by a conditional distribution. And then if I have 2 different latents, so I've got like a p of lambda 1 given x and a p of lambda 2 given x, then it's underdefined what p of lambda 1, lambda 2 given x is, right? Because I don't know what sort of correlations might exist between those. Unless one of those lambdas is a deterministic function of x, in which case it's no longer undefined, we're good, we're off to town, right? So basically what this is saying is any way of extending your distribution to add in this lambda 2, it's going to work, everything's going to apply here. All right, let's break there, and then we'll talk about, maybe do another example and talk about approximation.
About the time.
All right,
Are we going to get examples?
What was that?
Are we going to get examples?
Yes, first we're going to review what we hit so far. No, then we're going to review it with examples. So far, we've got this idea of like two different models. They agree on the distribution over observables, whatever those are, but they're using different latents sort of internally. The thing that defines a latent is sort of defined by its conditional distribution given the observables, but it's ambiguous how to combine them together into one model, unless one of them is a deterministic function of x, which under our conditions one of them is. Yes?
That does feel like it's throwing out some information about what would make a latent. Like,
Some information about what?
about what latents are. Like, if it's only defined by its distribution of the observables, you're not capturing the way they relate to each other.
If there is more than one latent in the model, then that's correct. So this would be talking about, and in fact, that's the thing we want to do a lot, is we want to talk about like the relationship between like this latent in my model and some other potential latents in someone else's model, while just like totally ignoring all the other latents in my model. So like if we then want to also talk about other latents in my model, we would have to, go further than this. Right. Then we said, okay, if these 2 conditions apply for one of these latents, for x1, say, sorry, lambda 1, then first we have that lambda 1 is a deterministic function of x. Therefore, we can do this extension unambiguously. Second, we have that that lambda is minimal over over latents that induce independence, maximal over latents that are invariant under. Man, I haven't introduced for sampling yet. Latents that you can compute from a subset of stuff, or sample from a subset of stuff. I'm going to introduce this lingo now. You can think of this as lambda prime is invariant under the distribution of lambda prime is invariant under the operation of resampling xi conditional on xi bar. That's why I use the phrase invariance. I'm not going to unpack that, but if I accidentally say invariance under resampling, that's why I'm referring to this diagram. Right. So if we have these natural latent conditions, both of these for lambda in one of the models, then we can say, all right, for any lambda in the other model, this latent our natural latent will contain strictly less information, or no more information, if the other latent induces independence, and similarly, no more information if the other latent satisfies this invariance condition. If the latents in both models, if we've got a latent in both models that's natural, then roughly speaking, we have isomorphism between them. More precisely, we have isomorphism between their standard forms, p of x given lambda. So they're giving us the same information about x. Okay. That's most of the sort of core technical pieces. Everything else from here is going to be examples, applications, extensions, that sort of thing. Okay? Yes?
Ask this, but maybe ask again for the crowd. Do they always exist?
These do not always exist. That's a good question. These are like intended to be sufficient conditions for a particular latent to be useful in this way. We may, depending on what people are interested in, we may go over some arguments that like they will usually exist in certain kinds of situations, and like what kinds of situations those are. Any other questions?
Well, in the exact form, they very rarely exist. We can give a criteria.
Correct. Yeah. So almost all of the interest is in the approximate case. All right. Let's do an approximate case then. So dead simple case. You've got a biased die and you roll it a bunch of times. Let's say you roll it 100 times, right? One of our agents is modeling this die as, having a bias. And yeah, so the bias is a latent here because the die rolls are the observables. The rolls are all independent given the bias, and you can get a pretty good estimate of the bias from all but one of the rolls, right? So this is a very simple case of like, it satisfies the independence condition exactly, it satisfies the invariance condition approximately. Another example, we talked about the ideal gas earlier. This one, both the independence and the invariance conditions are approximate. And how well they apply depends on the size of these little regions and the distance between them, right? So if I take like a bunch of little chunks of my gas, if those two chunks are very close together, then they're potentially not independent. They're going to be interacting a fair bit. As you get further apart, empirically, they end up being quite independent. Then the invariance condition is essentially talking about equilibrium. So I can estimate the temperature, the average energy of the whole gas by looking at some of the chunks. Depending on how big those chunks are, that'll determine sort of how many I need to look at to get a precise estimate. But for mesoscopic size regions, as they call them, like these things are sufficiently big and sufficiently far apart, we'll get both an approximate independence and an approximate invariance condition. A third example. Suppose we have a Markov chain. So we've got like y1, y2, ... and it's going to be a symmetric in time Markov chain. So the transition matrix from t to, I'll write it as a probability. P of yt given yt minus 1 is going to be the same for all t. So we've got a time symmetric Markov chain, right? And you've got your usual thing with Markov chains, right? You've got what do they call them? Ergodic subcomponents, right? So over time, if I pick a subset of these y's that are sort of separated in time, so let's say I take things that are big T steps apart, then those will be, there will be an approximately an approximately conserved quantity, namely which ergodic component it's in. And I can look at any of them to figure out which ergodic component it's in, because it's going to stay in that ergodic component. On the other hand, they will be approximately independent, conditional on that, because within the ergodic component you have mixing.
Wait, what is these T's?
That's just like I'm looking at some states of this Markov chain that are big T steps apart. So I'm giving it some time to mix within an ergodic component. Well, how many depends on eigenvalues of this transition matrix. In fact, the specific condition you need here is you need like 2 eigenvalues of this transition matrix to have a gap between them.
Yeah.
So that like you can get, there exists some time scale big T on which you have like mixing within some basically conserved ergodic components. And like how big that gap is then going to determine how well this approximation holds. Yes?
So to be clear, here not just the invariance, but also the independence is approximate.
Correct.
Okay, so sorry. The first one you gave was the bias of the coin.
Bias of a coin or a die, yeah.
The second was the temperature.
Yep.
And those are exact. Well, no. The first one is exact. The second one is approximate.
For the die, the independence is exact and the invariance is approximate. Probably not true for real dice. Probably for real dice, even the independence is approximate.
Okay,
But
and for the temperature, they're also both approximate.
yeah. So in most cases, they're going to be both approximate.
Okay, and then it's a non-ergodic stationary process.
Mm-hmm.
Or it is ergodic.
Ergodic stationary process. We're relative to a time scale. It is an ergodic stationary process. Yeah.
And what are the latent variables in the Markov chain?
So the relative latent here would be which ergodic component you're in. Yes.
In each of these examples, I'm struggling to imagine a second latent.
Sure. All right. Let's do that.
Sorry, if I'm not. So these T's could differ, right? The different like approximate ergodic components could have wildly different spectral gaps or mixing times.
That's correct. So effectively, what we'd be doing then is talking about latents over different x's. And that's like very typical here. Like if you're imagining 2 agents, they've got just like all sorts of latents in their world models, right? The main way you can imagine using this thing is these agents are looking at like some subset of observables or some subset of stuff where they expect that, first of all, the other agent is going to have the same distribution as them, and then they manage to find a natural latent over those specific observables. And then they can talk about how their latent relates to other agents' latent relative to those observables. Okay, what was the question that I was about to answer?
How we can imagine a second latent in these examples.
Right, second latent. Let's start with the bias of the die. One latent that induces independence would be the values of all the die rolls. The values of all the die rolls are independent, conditional on the values of all the die rolls. Another one would be the bias plus the outcomes of 2 of the die rolls. Both of those induce independence. A thing that is invariant for invariance, any invariant is going to be a function of the bias of the die roll in this case. So for instance, you could think about an indicator function saying whether the die is biased towards larger numbers or smaller numbers. So whether its expectation is greater or less than the mean of a fair die. That would be an invariant. Yeah.
You mean, is it bigger than half or not?
For a coin, it would be a half. For a die, it would be 3 1/2. Assuming a 6-sided die. Another example, let's say in this like physicsy picture, the temperature is a latent that induces independence. A latent that has some more information in it would be like the temperature and also let's say the average rotational energy or rotational momentum about some point over in like this chunk of the gas. not a particularly interesting one. Or alternatively, like the temperature, and similar to the dye, we can just like append states of X, parts of X to it. So we could say like, well, the temperature plus the entire microstate of this chunk of the gas. That induces independence.
So what's the relationship between these nice latents and sufficient statistics of the general distribution?
So first of all, sufficient statistics, as they're usually defined, are doing a slightly different thing. You're usually looking at them in an infinite limit. You can do approximations with them, but it's like kind of awkward. Second, the invariance condition in particular is load-bearing here. So for a sufficient statistic, you want to have, how do I say this? Actually, you know what? We haven't introduced the thing we need to answer this question properly yet. In the approximate case, a big thing that happens, we said lambda is a deterministic function of the x's. In the approximate case, that becomes an approximately deterministic function of the x's. Which is where we really diverge hard from a sufficient statistic. So the sufficient statistic is just always a deterministic function of the variables. Here we'll see that this like deterministic function that I wrote over here, that deterministic function still ends up being approximately giving the distribution of any approximate natural latent. But like you have to sort of be very careful about exactly which approximations you're applying where to make that work. Another way to put this is the temperature is not actually isomorphic to average energy. In particular, you can see this in systems with very few particles. In that case, if you're defining the temperature statistically, you'll still have some uncertainty over temperature once you update on the momenta and energy, of all the particles in the system. So it's like not actually quite a deterministic function of the low-level variables. Yeah. So mostly the answer is there's sort of conceptual mess in the approximations, which ends up being very important for making the approximations work well. Yes?
What about a mixture of Gaussians?
What about a mixture of Gaussians? All right, we'll do that one now. So mixture of Gaussians is starting to introduce some like additional pieces. The main place where a natural latent enters in the mixture of Gaussians is conditional on the cluster labels. You have like each of the points in a cluster is independent of the other points given the statistics of that cluster, right? So within this cluster, I have some sort of shape parameters, mean and a variance or something like that. That's not very Gaussian, whatever. I have like a mean and a variance defining this cluster. Conditional on that mean and variance, all of the points are independent, and I can estimate that mean and variance from like all but one of the points in the cluster. So conditional on the cluster labels, we have a natural latent. Right, the approximation, yeah. I guess we better get that in real quick. So the high-level sketch here is assume that this holds within epsilon. What do I mean by holds within epsilon? The operationalization we usually use is that there is a small KL divergence between whatever actual distribution I have over x and lambda and this factored distribution. So dKL within epsilon. But you can use other notions of approximation, and like the general thing I'm about to show should generally carry over for reasonable notions of approximation. So like all of these hold within epsilon, or you can make them different epsilons or whatever. And the point is, at each step of this proof, we can say like, all right, if all of these hold within epsilon, then this guy is going to apply within 3 epsilon, because we have to use each of these epsilons once. This guy is going to hold within then 3 epsilon. This guy is going to hold within 3 epsilon. This one, we need to use each of these guys n times. In the simplest way of doing it, we can shave a few epsilons off of there, but like simplest way of doing it, you have to do it n times, you get like 3n epsilon. That's sort of the structure of the thing. So you just sort of propagate your epsilons through the proof and get an approximation. Yes?
I'm going to say some stuff which is only approximately true.
Sure.
But the thing that characterizes agents is that they have goals.
Yeah.
And to have a goal is to take something that's pretty unlikely and make it more likely.
Reasonable operationalization.
And it seems to me like...
Wait, what if you fail to achieve your goal? Or what if you're just like bad at stuff? Do you then not have goals?
I'm specifically worried about agents that are good at stuff.
Okay, go on.
In those cases, I'm worried about cases where your assuming away the approximations actually matter.
Which approximations?
These epsilon units.
What? I'm not assuming them away. Like what we get here is that if these hold within epsilon, then like the final thing holds within like some epsilon. So like these are bounds. Like we're not assuming away the epsilons. We're explicitly saying like, all right, if you're within these, then your conclusions have a bound on them. They can only be so bad. What am I assuming away here? Like, are you saying you're concerned about the case where like these don't hold to within epsilon?
No, I'm concerned about the case where these hold within epsilon, but the thing knows that and wants it to be not the case that it's latent and my latent map onto each other.
Then too bad for the thing. That's how proofs work.
I failed to communicate, I think.
Does your epsilon carry through to the claim that there's an isomorphism between latents?
Which part? The answer is going to be yes, but which part?
Yeah. Let's see. The claim that there's some isomorphism between lambda 1, lambda 2.
Okay, if we're talking about the isomorphism, then that would be the case where naturality condition applies for both of them.
Right.
And in that case, yes, carries through. I believe that will have, like we just have these epsilons here, it's gonna scale roughly with n. Yeah. Also, I should mention, note that the like quick hand wavy run through of the approximation, we got the error on the conclusion was scaling with n. That's not great. The main way to improve that is to strengthen the invariance condition. So if you can resample, if you can drop more than just one variable and still get roughly the same distribution on lambda prime, then you can pretty quickly knock down the error down here.
Yeah, so just to restate, basically we can sort of sample lambda prime from lambda or lambda from lambda prime, and this gives close in a KL divergent sense to what it actually is.
Bingo.
Could you say what the, so if you, let's say you can drop a fraction alpha of the variables, what kind of error do you end up with?
Then that's gonna divide, that's gonna divide your error by like 1 over alpha, or 1 over 1 minus alpha. Yeah, that's it. So like an actually pretty common case is you can just compute an invariant from any one of the xi's, right? So like, for instance, this case with an ideal gas, you can look at any one little chunk of the gas and get a good estimate of lambda. And then, like this is gonna be real good, right? This is gonna be of order not dependent on n, just epsilon. Or similarly with a die, if you only need 100 rolls to get like the precision you want, then as n goes up, you still only need O of 1 rolls to get the precision you want, so this guy's gonna be real nice.
So,
rock, paper, scissors.
I'm gonna go because I think this is a good question.
Yep.
We've got like 1 minute left, but I would like to ask you to briefly philosophize about the significance of these ideas.
Yes.
Yeah.
Sure. So the broader like agenda this is operating inside of is the idea of abstractions that are natural in some sense, right? So these are like a particular set of conditions under which some latents, some abstractions operationalized as latents, are going to be natural in like the sense we've shown, right? This is not yet, if you just use this is not going to get you all the way to end use cases, right? And if you want to get to more, if you want to do like more typical sorts of structures, real world structures that humans think about or talk in terms of, then you need to like further build on top of that. But the idea is this is sort of the, insofar as we're grounding out in natural latents, we have some machinery to transport them to other models or to like expect other models to end up with compatible things in their ontologies. Is that sufficient philosophizing?
Yeah, thank
Cool.
you. Okay, let's thank the speaker.